I'm going to present Instance, the Italian seismic dataset for machine learning. This is the outline of the talk. It's subdivided into motivations, the dataset with compilation, metadata features, waveforms, and then we go to comparison with other datasets and conclusion. This presentation follows from an article that we have submitted. It's now currently under revision. Motivations. Deep machine learning applications have been showing all their potential in several fields of science. To this regard, several machine learning software platforms are contributing to help data researchers and professionals to perform sophisticated analysis. Basic to this are well-organized datasets, which exploit all the potential of these software platforms. Seismology is a data-rich field that features raw data and databases that include both parametric measurements and parameters that are obtained from the analysis, like location, magnitude, etc. The main goal of this work is to make available a data set for Italy that can be used for several different studies using machine learning analysis techniques. Topics in seismology with machine learning. There have been, in the past years, in the very recent years, very many articles and studies that addressed detection, peaking, earthquake location, magnitude and fault mechanism, earthquake early warning, inversion and tomography, estimation and prediction of ground shaking, analysis of massive seismic waveform datasets, noise removal, and many other fields. Topics in seismology will be addressed with machine learning in the next future. Qualified benchmark datasets. These are really main ingredients in doing machine learning. Benchmark datasets and competitions are playing an important role in driving process and innovation in machine learning research. High quality benchmark datasets have two key benefits. One is enabling rigorous performance comparisons, and two, producing better models. Competitions are common practice in machine learning to report performance on new algorithms on standard data sets. For example, 464 completed competitions have been carried out on Kaggle since 2011. In seismology, it was launched a machine learning competition for laboratory earthquake forecasting, and there is the Seismo Olympics in 2017. Benchmark dataset in seismology. There are a number of benchmark datasets already available. And one important thing that I have emphasized with in green is the SeisBench. SeisBench is the toolbox to unifying the application of machine learning pipelines to seismic data. This is very important in order to have the ability to switch to other data sets using the same model or vice versa. Instance. Now we go through the compilation of how Instance was prepared. So we took data from 2005 to 2020 from the IDA INGV node. This total instances are about 1.3 million of three-component traces for waveforms and noise. Waveforms constitute about 90%, and 10% are for noise. This is a map on the left of the 54,000 earthquakes that have been selected that well represent the Italian seismicity in these past 15 years. On the right-hand side, we show the moment tensor for those earthquakes that are included in the dataset that had magnitude more or less greater than 3.5. Metadata. Metadata are really of crucial importance when doing machine learning. We have associated 115 metadata to each event trace and 46 metadata to each noise trace. Our metadata are basically for the event of 4 types: source, station, trace, and path. And for the noise, just station and trace. On the right-hand side, what you see here is the distribution of channels, networks, polarities, magnitudes that are within instance. Magnitude versus distance. This is a distribution of the earthquakes according to magnitude and distance. What you can see is that the great majority of the earthquakes that are included in instance are between magnitude 2 and 3 and within 250 kilometers. But we do include earthquakes down to almost 700 kilometers and up to magnitude 6.5. This is an example of travel time data in which you can see the distribution of the travel time data in 4 different distance ranges between 0 and 700, 0 and 200, 0 and 100, 0 and 40 kilometers. So what you can see already from this picture, for instance, between 0 and 200 kilometers, the PG and the PN phases, or what you can see in the 0 to 40 kilometers, the spread that is observed for both P and S that are an exemplification of the 3-dimensionality of the structure in Italy. Other metadata include signal-to-noise ratio, and here is the distribution on the left for the 3 component, or on the right for the signal-to-noise ratio according to distance and to source magnitude. Another thing that's important of instance is that we included both the intensity measurements of PGA, PGV, etc., in ground motion units and in counts. So here are on the left all the ground motion units for earthquake greater than equal to magnitude 2. And on the right-hand side, what you see is the just for the magnitude 3 earthquake. Quality control metadata. Some of the inclusion of so many metadata is because we want to have complete control on the data set to be selected. And here on the left-hand side, there are some standard measurements that are taken from the counts waveforms, which are like RMS, max, min, lower and upper quartiles. So the user can actually choose which data to use. On the right-hand side, in order to cross-check what the quality of the data set has been prepared, we ran both 2 different automatic picking algorithms, the EQ transformer and GPD. And what you can see here, highlighted in blue and in orange, is that our selection of 1 earthquake per trace is satisfied in most of the cases. Conversely, for the noise, what you see is that similarly, we get also no earthquakes or very few earthquakes for the noise traces, as we were seeking from the very beginning. These are examples of the waveforms. What you see here is that we have selected randomly for each row. What you see is the random selection according to the criteria that are shown on the right-hand side. The 3 top panels show the distribution in different magnitude ranges, ranging from magnitude 2 and above. And in the 3 panels down to the bottom, what you see is another criteria of selection based on the signal-to-noise ratio. Overall, what you can see is that the quality of the data set is definitely quite satisfactory. Here we enter in the comparison between the instance and other seismological machine learning data sets. We have put arrows for what are basically the main differences between instance and other data set. This is the number of metadata, both for events and noise. The fact that we have trace lengths which are 12 seconds length, 120 seconds length, sorry. And we provide both units in digital counts and in physical units. Also noteworthy is that we have on the order of 21 as a average number of receivers for each earthquake. And overall, the data set includes something like 38,000 hours of time recordings for the events and 4,000 for the noise. Conclusions. Instance is the first data set designed for the application of machine learning methodologies in Italy. Provides a benchmark for developing improved techniques for earthquakes and ground motion characterization. The data set consists of about 1.3 million, 120 second long each, 100 Hertz sampling, 3 component traces subdivided into 1.2 million events and 130,000 noise traces. The traces have been assembled within an HDF5 formatted volumes and to facilitate the analysis and are included in SeisBench. 115 metadata being grouped together according to source, station, trace, and path. For each trace, the magnitude range is between magnitude 0 and 6.5. The total number of hours is 43,000, an average of 21 3-component traces, and it can be used for several things in machine learning: detection, location, size estimation, denoising, and ground motion estimation, among many others. These are the acknowledgements. Thank you for the attention.